Here's the first new topic for discrete probability, and it's actually probability distributions. A probability distribution is essentially just probabilities summarized in a table, and we're going to illustrate that with this example here. The amount of goals scored by Liverpool in a match. I'm a Liverpool fan. Yeah, obviously you can see the number of goals is not that high, right? Because Liverpool, not so good last season. The amount of goals scored by Liverpool in a match is described in the probability distribution below. So we'll have an interpretation, or we'll do an interpretation of this table and what the numbers actually mean, and try and understand how good Liverpool is. And obviously I said they're not that good, but hopefully they do improve this season. Yeah, anyway, I'm just going into flashbacks of the depression from last season. So we can see we have a top row here and a bottom row here defined by those leading variables. Now I'm just going to switch sides here. This variable here, x, lowercase x, that represents the possible numbers for the number of goals. In this case, we have capital X goals is just like the general variable describing the number of goals. The lowercase x is describing the specific cases, or the specific, how do I say? Yeah, just the different possible values for the number of goals. But x in general, capital X, just represents the number of goals. So this is the possible values for x, capital X. And we denote the possible values of capital X as lowercase x. So for example, if I wanted, you can see here the probability on the next line is probability of capital X equaling lowercase x. So the lowercase x is the possible numbers. So for example, if you wanted the probability of x is equal to 0, that's just 0.26. That's how the table works. It just corresponds to each other. I'm just going to flip sides. They just correspond to each other. So the probability of x equals 0, like that, is equal to 0.26. And you can read off the rest of the probabilities as well. So probability of x is equal to 1 is 0.49. Probability that x is equal to 2 is equal to p. That's unknown right now. But since it's unknown, we're going to talk about how we actually can find it. So it's pretty self-explanatory. I should just write here, they're the probabilities. Pretty self-explanatory. But to find p, what we have to do is consider that all of the possible outcomes are in this table, and that's a really fair assumption because a probability distribution wouldn't be complete without all the possible outcomes. So for example, Liverpool doesn't have a probability of scoring more than 2 goals. They don't have a probability of scoring 3 goals, 4 goals, whatever, right? And I've done that on purpose because they haven't been playing that good, but in this case it makes it a lot easier to calculate because you only have 3 possible outcomes. So in this case, how do we find p? Pretty obvious. It's a probability condition, or I guess just a restriction on probability and numbers. It's the fact that probabilities and all the outcomes should add up to a probability of 1. So how I write that in this format is, let's just do sum of probability x is equal to x. That's just a long way of writing this, by the way. So probability of capital X is equal to lowercase x. I mean, you could just do the sum of probabilities is equal to 1, but I want to use the proper notation. So I just say sum of probabilities using that notation from this table is equal to 1. Okay? So what I get is 0.26 plus 0.49 plus p is equal to 1. Therefore, p is equal to 1 minus 0.26 minus 0.49. Let's do some quick maths. 1 minus 0.26 is 0.74. Minus 0.49 is equal to 0.25. Yeah, equal to 0.25. Cool. So this value here is equal to 0.25. I don't have to rewrite it in the table. I don't have to cross it out. Usually this table would be printed out and given to us if you're doing a test or an exam. So we could just leave it as p, but just note that p is equal to 0.25 for any further calculations. Now the second part of this question, determine the probability of x being equal to 2, given that x is greater than or equal to 1. So a conditional probability. In this case, what we do is just use the formula, intersect x is equal to 2 with x is greater than or equal to 1. And divide that by the probability that x is greater than or equal to 1. Now the intersection between x is equal to 2 and x is greater than or equal to 1, you can just see visually that it's x is equal to 2 because x is greater than or equal to 1 includes this value, and then x is equal to 2 is obviously just a subset of that. So this is just going to be equal to probability that x is equal to 2 divided by the probability that x is greater than or equal to 1. Now, x is equal to 2, we just found was 0.25 or p. x is greater than or equal to 1 is 0.74, because 0.49 plus 0.25. So therefore, this value is 25 over 74. You can see what I've done here is just multiplied the top and the bottom by 100, and that's a really easy way of cancelling them out. And this can't be simplified any further because 25 only has multiple of 5, and it doesn't have, apart from 1 and 25, obviously. Sweet, we'll rub this out now, and we'll go on to a couple more examples, which is kind of an extension of discrete probability distributions. Now, for any different type of probability distribution, in the future we're going to learn different types such as continuous and normal distributions. They all have two characteristics that are really important for describing the distributions. The first one we're going to talk about is E of x, which stands for expected value, okay? So E of x here, just going to write down, it stands for expected value of x. Expected value is just another way of saying the average or the mean as well, okay? Average or mean, okay? So what does that mean in terms of this context of the amount of goals scored in a match? So if I calculate E of x, it's just the expected number of goals or the average number of goals that we expect Liverpool to score pretty much. So how to calculate it for a discrete probability distribution, and by the way, the process is different for different types of distributions. How we calculate it is we sum the multiplication of these pairs. So for example, I'm just going to write down the formula first. So that symbol for sum, and then x, which is the possible outcome multiplied with the corresponding probability. Okay, so that's the fancy way of writing it. This is the formula on the formula sheet, but how we actually interpret this from an algebraic standpoint is we multiply 0 with 0.26, and then we add 1 multiplied by 0.49, and when we plus 2 multiplied by 0.25. So I'm just going to write that all out. Plus 1 multiplied by 0.49, plus 2 multiplied by 0.25. So 0 multiplied by that, obviously just 0. 1 multiplied by 0.49 is 0.49, and then this is 0.5. So our final answer is 0.99 goals. Now, does it make sense that the number of goals that it's expected is not a whole number? Well, in this case, it is, because it's a statistical average. So we wouldn't expect to round it or anything, because expected value should be, you know, like, it is never likely that an average, a statistical average, is going to be an exact whole number. Even in this case, if we're going to have whole number outcomes, because it is a probabilistic thing, it's fine to keep it as a decimal, and it's actually expected that we do keep it as a decimal. So on average, Liverpool is scoring just under 1 goal per game. And based on the probabilities, that kind of makes sense. And you can kind of see the numbers are slightly, very slightly skewed in the left direction, because we have 0.26, 0.49, and 0.25 here. So the numbers are slightly skewed to the left, very slightly, and the left, I mean the left of 1, okay, the left of the middle value. So this kind of makes sense if you look at the probabilities. And yeah, again, as I mentioned in the previous part, or the previous video, the numbers should always make sense when you look at the context. So in this case, this 0.99 does make perfect sense, because the numbers are slightly skewed to the left-hand side of the table. Sweet. Okay. Now we're going to go ahead and calculate the variance. Hopefully the expected value, or the average or mean value, does make sense from a probability standpoint. The variance, I mean, you can kind of just imagine this word. I just use a different color actually to separate these working out. This is the variance. Variance, can't write. So the variance is a measure of the spread, okay? So a spread of a distribution. What the spread means is how far the possible outcomes, you know, are literally separate from each other in the table, or separated from each of the other values. So I'll show you two examples of maybe a high spread versus a low spread distribution. So for example, if I had to change these probabilities, right? Let's do two separate possibilities. So we have 0, 1, and 2. I'm not going to write out the full table, but 0, 1, and 2. Let's say we had 1/3, 1/3, 1/3. And then we verse that, 1, 2, 3, with 1/10, maybe not 1/10, we'll do 2/10, 4/10, 4/10. Okay, so we have two different distributions. We can see this one is equally distributed, and this one is not equally distributed. You can see the outside ones are much greater, pretty much double the middle value. Which one do you think has a higher spread? In this case, this one would have a higher spread because you have further numbers away from the middle. And you expect for each of these, by the way, the expected value, if you did calculate it, is the middle value exactly. I've done that on purpose because the variance is the spread from the expected value. So you can see in this case, you have higher probabilities away from the expected value. This one has lower probabilities in comparison to this one. So this one would have a higher variance, and this one would have a lower variance in comparison to each other. Okay, it's just an important thing to note. That's what the variance actually means from a statistical perspective. And if you did plot these, then the variance would just mean like how far away the graph is, like in terms of the peaks away from the expected value. But as long as you understand that it's a measure for spread, so this one is more spread, this one is less spread, then that's the most important thing that you need to know. So how do we calculate it? The formula for variance is e of x squared minus e of x squared on the outside. They're not the same thing. E of x squared is the same calculation that we did above, but we just square the outcome value. So for example, if we wanted to calculate e of x squared, I'll just do an arrow just to indicate that this is the e of x squared calculation. It'll be the same as before. It'll be 0 squared multiplied by 0.26 plus 1 squared multiplied by 0.49 plus 2 squared multiplied by 0.25. So 0 multiplied by 0.26, that obviously that's not even part of our calculation. 1 squared doesn't make a difference, so it's just 0.49 plus 2 squared, which is 4 multiplied by 0.25. So that's the part of the calculation that slightly changes. 4 multiplied by 0.25 is 1, so this value would be 1.49. And by the way, this was the calculation for e of x squared. Again, it's just the outcome squared multiplied with the probabilities, and then we'll add it together. Now, e of x squared is equal to 0.99, or the expected value just squared on the outside. 99 times 99, I actually don't know what that is. Let me do a quick calculation. Okay, I've got the trusty app calculator on my laptop. We've got 0.9801. I'm just going to make it 0.98 just to make it easier to calculate things. So therefore, the variance is equal to 1.49 minus 0.98, which is equal to 0.51. Yeah, cool. Cool, the variance is equal to 0.51. Now, in terms of like how we interpret the number, it's not as easy to interpret as the expected value. The expected value is clearly a finite thing that we can compare with our statistical values. The variance is a bit harder to compare because there's not a kind of a set way of, saying, okay, is this number correct? Does this spread of 0.5 make sense? It can't really interpret it from that statistical standpoint, comparing it with our discrete values. So we kind of just say, okay, the variance, we probably did the calculation right if you use the formulas right, so it's going to be equal to 0.51. Now, a key thing to note with variance is that you might recognize spread, the term spread, kind of being associated with a term called the standard deviation, especially if you've done further or any sort of statistics content in the past. So variance is actually related to standard deviation. Standard deviation is that. So if our standard deviation of that, it's equal to the square root of variance. Okay, so this is standard deviation, and this is obviously the variance. So that's how they're related. The standard deviation is just the square root of the variance. So if the question asks you to calculate the standard deviation, you just square root this variance value and you would get the standard deviation. Now there's a couple of useful properties of standard deviation, but they don't really apply to a discrete case. And the reason for that is because a discrete case, you can see here, we've only got 3 possible outcomes. And the properties of standard deviation, such as, you might have heard of the 68, 95, 99.7 rule. If you don't know it, it's fine. It's going to be taught in a later topic in methods. But if you're kind of curious, does that apply in this case? Well, not really. It should apply, theoretically, but because we only have 3 outcomes, we don't have a big sample space. So you can't really see those properties being exhibited. But if you did have a wider sample space and you did have more values that were maybe normally distributed, you would more so see the properties of standard deviation being applied.